Picture this. You are drifting in space, silent, weightless, wrapped in the kind of darkness that makes midnight look like a stadium concert. Ahead of you is a black circle cut into reality itself. Not a planet, not a star, not even a hole in the usual sense. A black hole. And surrounding it is not just darkness, but warped light, bent time, and the last boundary in the known universe where the rules we trust begin to slip through our fingers. Then you get closer, closer. And now you are approaching the most famous border in astrophysics, the event horizon. The line where escape stops being difficult and starts being impossible. According to NASA, the event horizon is not a solid surface, but a boundary around a black hole beyond which nothing, not even light, can escape. Tonight, we are going all the way to that edge. What is a black hole really? What would you see near the event horizon? Would you be stretched into cosmic spaghetti before you crossed it? Would time slow down? Would you hit something? And once you pass that border, what happens then? Ladies and gentlemen, welcome to the most dangerous sightseeing trip in the universe. Let's clear the fog first. A black hole is not an interstellar vacuum cleaner roaming the galaxy like it missed therapy and chose violence. It is an object, an extremely dense concentration of mass whose gravity becomes so intense that once you cross a certain boundary, nothing can get back out. ESA and NASA both describe black holes this way: gravity so strong that not even light can escape. That boundary is the event horizon. And this matters because people often imagine black holes as giant mouths in space, chewing galaxies like popcorn. Not quite. If the sun were magically replaced by a black hole of the same mass, Earth would still orbit at roughly the same distance. We would freeze, yes, which is rude, but we would not be sucked in just because the object became a black hole. The gravity far away depends on mass, not on whether the mass is a star or a black hole. So the black hole is not some magical devourer with bonus gravity at every distance. Its terror is more elegant than that. It becomes truly monstrous when you get close. Very close. Close enough that space-time itself stops acting like a calm highway and starts folding like a cheap lawn chair. Now here's where things get weird. The event horizon is not a hard shell. It is not a glowing force field. It is not a cosmic brick wall with a sign that says, "Abandon hope ye who enter here." NASA explicitly notes that the event horizon is not a surface like Earth's or the Sun's. It is a boundary. A one-way border in space-time. That means if you were falling toward a black hole, you would not smack into the event horizon like a bird hitting a glass window. In your own local frame, your own immediate experience, crossing it might feel strangely uneventful, at least for a sufficiently large black hole. And that is one of the cruelest jokes in the cosmos. Because the most important line you can ever cross might not announce itself at all. No alarm, no cosmic buzzer, no voice from the dashboard saying, "You have reached your destination." Just the quiet transition from "still maybe" to "absolutely not." From far away, a black hole is not just black. Around many black holes is hot, infalling matter called an accretion disk, and that material can glow fiercely as it heats up. NASA notes that accretion disks around black holes can emit enormous amounts of energy, including X-rays. But the visual madness comes from gravity bending light. The black hole's gravity redirects nearby light through gravitational lensing, producing a dark central region often called the black hole's shadow. NASA explains that the event horizon traps light crossing it, while nearby light is bent, creating a shadow roughly twice the size of the actual event horizon scale boundary. The Event Horizon Telescope similarly explains that we do not photograph the horizon directly, we see the effects of light and hot matter around it. So if you approached one, the universe behind it would smear, distort, wrap, and brighten into impossible arcs. Stars would appear where they should not be. Light from behind the black hole could bend around it and show up from the sides. Space would look like it had stopped obeying geometry and started improvising jazz. Which, to be fair, is exactly what strong gravity does. Ah yes, the pasta course. Spaghettification is the nickname for what happens when tidal forces become extreme. Gravity pulls harder on the part of you closer to the black hole than on the part farther away.
NASA describes this growing difference in gravitational pull as an object approaches the event horizon, and notes that matter can be stretched, squeezed, and torn apart near black holes. So your feet feel more pull than your head. You stretch, and stretch, and stretch. You become the universe's least appetizing noodle. But here's the important twist. Whether you get shredded before the event horizon depends on the size of the black hole. For a stellar mass black hole, the tidal forces near the horizon are so intense that you would likely be destroyed before crossing it. For a supermassive black hole, the event horizon is much larger, and the tidal gradient at the horizon can be much gentler, meaning you might cross the event horizon before the stretching becomes fatal. NASA's black hole visualization and other astronomy references reflect this distinction. That is right, a small black hole is more immediately rude. A supermassive black hole is more polite. It lets you cross the point of no return first, then ruins your life afterward. Now we step into Einstein's territory. According to general relativity, gravity is not just a force pulling on objects. Gravity is the curvature of spacetime itself. ESA notes that black holes and related phenomena are predictions of Einstein's general relativity. Near a black hole, time does not behave the way your watch wrist emotionally expects. To a distant observer, someone falling toward a black hole appears to slow down as they near the event horizon. Their light is stretched to longer wavelengths and dimmed. In practical terms, they seem to freeze and fade near the edge, rather than cleanly cross it in view of the outside observer. NASA's recent visualization of a plunge toward a supermassive black hole highlights these relativistic effects. But from the falling person's own perspective, they keep going. This is one of the most mind-bending splits in all of physics. You, the falling traveler, experience continued motion inward. They, the distant observer, never really watch you cross in ordinary visual terms. So which one is real? Both. And if that bothers you, congratulations, you have successfully made contact with relativity. Now let us go to the exact question in the title. What happens at the event horizon? Here is the cleanest answer science can currently give. At the event horizon, you cross a boundary where all future directed paths lead inward. The event horizon is the point of no return. Once matter or light passes through, it cannot escape back to the outside universe. NASA, ESA, and the Event Horizon Telescope all describe the horizon as that boundary. Notice something important. The event horizon is not just where gravity is strong. Plenty of places have strong gravity. It is where space-time is warped so radically that going outward stops being a future option. Inside that boundary, moving toward the center is not like choosing north instead of south. It becomes more like moving toward tomorrow instead of yesterday. That is the terrifying beauty of it. Outside the event horizon, escape is hard. Inside the event horizon, escape is not hard. It is undefined. And here we arrive at the edge of known physics. Classical general relativity says you continue inward toward a singularity, a region where the equations predict curvature becomes extreme and our current theories break down. NASA educational materials describe the singularity as the place classical descriptions send matter after crossing the horizon, while also making clear that what truly happens inside remains unresolved. That last part matters. Science does not currently have a complete, experimentally confirmed answer for what happens at the deepest interior of a black hole. This is where people online often leap out of a moving vehicle into fantasy. Portals, other universes, time tunnels, cosmic USB storage for dead astronauts. Maybe not, or maybe something even stranger. But responsibly, the current position is this. General relativity predicts an inward collapse toward a singular end state, while quantum physics suggests our present understanding is incomplete. NASA states plainly that once matter passes the event horizon, we do not yet know exactly what happens. That is not weakness. That is honest science. The map ends here, and beyond that edge, the equations begin to argue. Problem: the universe's greatest cliffhanger. Now let's go one level deeper into the rabbit hole. Black holes create one of the nastiest problems in theoretical physics. What happens to information? If something falls into a black hole, and the black hole eventually evaporates through Hawking radiation over absurdly long timescales, does the information about what fell in disappear? Quantum mechanics hates that idea. General relativity shrugs and says, I run gravity, not your filing cabinet. Nernst's tension is known as the black hole information paradox. It is one of the major unsolved problems in modern physics, and one reason black holes sit at the crossroads of gravity, quantum theory, thermodynamics, and the deep structure of reality itself. So when we ask what happens at the event horizon, we are not only asking about a place in space, we are asking whether the universe forgets, and physics, so far, has refused to answer cleanly. Which is both infuriating and, let's be honest, spectacular. Let's land this ship before it also crosses the point of no return. The event horizon is more than a feature of black holes. It is a philosophical border, a line in the universe separating what can still affect us from what never can again. A one-way curtain, a cosmic exit with no entrance. It tells us that space is not empty stage scenery, time is not universal, light is not guaranteed freedom, and reality is no obligation to feel intuitive to primates who only recently figured out fire and soup. At the event horizon, physics does not exactly break. It reveals that our everyday instincts were never built for this territory. Closing. So, what happens at the event horizon? Here is the answer, stripped clean. You do not hit a wall. You cross a boundary.
From the outside, you appear to slow and fade. From your own perspective, you continue inward. In a small black hole, you may be torn apart before you get there. In a supermassive black hole, you might cross first and die later. And after that point, according to everything we currently know, no signal, no light, no message, no final regret-filled voicemail comes back out. The event horizon is the edge of return, the boundary of communication, and one of the clearest signs that the universe is stranger than myth, colder than poetry, and somehow more beautiful than both. And the wildest part? We are still learning how this story ends. If this bent your brain in half, type horizon in the comments. And if you want more stories where science starts sounding like prophecy, and the universe behaves like it was written by a genius with a dark sense of humor, subscribe. Because next time we go deeper, and deeper around here is never metaphorical.